Hello chemists, this is Ms. Placino and you are watching Screencast 6.3 on mole conversions. Today's lesson is really going to be focused on using the mole to convert between units. We already know that the mole is able to connect some units that otherwise seem unrelated. For example, we talked about in previous lessons how 1 mole is equal to a number, 6.02 times 10 to the 23rd items or things. And usually when we say things, we're talking about extremely small pieces of matter, such as atoms or molecules. In the previous lesson, we talked a little bit about molar mass. And we know that that is the mass in grams of 1 mole of a substance. So hopefully it goes without saying that different substances are going to have different molar masses. For example, something like water, H2O, is going to be equal to the mass of 2 moles of hydrogen atoms plus the mass of 1 mole of oxygen atoms. And that's about 1 gram times 2 plus 16 grams times 1. And so a mole of water is going to have a mass of roughly 18 grams per mole. If I compare that to something else, say methane, CH4, goodness, why does it keep doing that? We know carbon has a mass of about 12 grams plus 1 gram times 4. Mass of the 4 hydrogens gives us 16 grams per mole. So finding molar mass or using molar mass to convert is a little bit more work, as we have to go through and figure out what the actual molar mass of that compound is. But again, today is going to be about using these different factors to convert. So let's get into today's lesson. And let's start with molar mass. Here's another way to represent it, and I think that this might be more useful as we're doing dimensional analysis. The molar mass in grams of a substance over 1 mole. So for example, I can say I have a mole of water or I have 18 grams of water. They are stating the same exact quantity, it's just in 2 different means of expressing it. So let's see if we can use this to convert between units. Let's say you have 19.3 grams of P4 and you're interested in converting that into moles. Well, I can't just use this conversion factor the way it's set up. I have a little bit more work to do. I have to use my reference table, specifically the periodic table, and figure out how much 1 mole of P4 would weigh. Phosphorus has a molar mass pretty close to 31 grams per mole. Okay to round in that case. So 4 times 31 is going to give me a molar mass of approximately 124 grams per mole. And I think I mentioned it before, but when you're calculating molar mass, you really don't need to show your work. I trust that you can add and multiply in your calculator. So I know that I've got 19.3 grams of P4. I want to get to moles, so I'm going to use this fraction. Let's represent that in a little bit different way, to get grams to cancel out and to leave me in a unit of moles. Hopefully we can tell the way things are set up, and I'll put this over 1 to help keep things organized, that we want to put grams in the denominator and put moles in the numerator. So we know that 1 mole is going to have a mass of roughly 124 grams. Grams of P4 can then cancel out, and it'll leave me with moles of P4. When I enter everything into my calculator, I come up with 0.156 moles of P4. And I should just do a quick sanity check and make sure that my answer makes sense. I've got 19.3 grams. I know that a full mole of P4 weighs 124 grams, so I definitely have less than a mole. All right, go ahead and try one out on your own. See if you can convert 2.98 moles of calcium hydroxide into grams. All right, you can check your work against what I've got on the screen. I've got 2.98 moles of calcium hydroxide, and I'm interested in converting that into grams. First, I need to find the molar mass of calcium hydroxide. I was pretty specific with mine. I've got 74.09 grams. I need to set this up so that mole cancels out, and that I end up with an answer in grams. And this will do the job. 2.98 times 74.09 grams over mole will leave me with 220 grams of calcium hydroxide. So in previous lessons, we've shown you how to use Avogadro's number, the definition that 1 mole is equal to 6.02 times 10 to the 23rd things to convert. We just used molar mass to convert. The last one that you really need to be aware of is molar volume. Molar volume is most useful when we are talking about gases. This really only applies to gases. We can't use this for liquids or solids. It's just gases only. Please make a note of that. It turns out that at standard temperature and pressure, we call this STP, and standard temperature and pressure to a chemist is 1 atmosphere of pressure. That's what we exist at sea level. And standard temperature is defined as 0 degrees Celsius or 273 Kelvin, one and the same. But under those conditions, it turns out that a mole of any gas, doesn't matter what we're talking about, oxygen, carbon dioxide, nitrogen, helium, hydrogen, regardless, occupies the same volume. Again, gases only. We were talking about gases under very specific temperature and pressure conditions. And it turns out that 1 mole of gas at 0 degrees Celsius and 1 atmosphere of pressure, also known as standard temperature and pressure, occupies 22.4 liters of space. I know this is like the 3rd time I've said this, but I see students making mistakes with this all the time. This really only applies to gases only. You cannot use this for liquids. In order to do any sort of mole work with liquids, if you've got a volume, you also need to know the density. So please make a note. Molar volume is for gases only. Let's try some practice problems. Here's another way to represent that 22.4 liters is equal to 1 mole. You don't need to be this specific when you go to make the conversions, but I just wanted to make sure that we're all on the same page. So let's try one out. We've got 6.53 liters of neon at standard temperature and pressure. Now the fact that it's neon isn't going to change anything in this case because we're trying to convert out of liters into moles. And regardless the identity of your gas, 22.4 liters of that gas at standard temperature and pressure will be equal to 1 mole. So I can write 6.53 liters, and I'll put it over 1 to help keep things organized. Oops. I know that 22.4 liters of gas equals 1 mole. I want liters to cancel out, so I'll put that in the denominator. And I'll put 1 mole up in the numerator. Liters cancel. I'm left with an answer in moles. And when I go through and perform the calculation, I end up with 0.292 liters. Oops, just made a mistake. Sorry about that. 0.292 moles of neon gas. Go ahead and try one on your own. Pause the video and we'll pick up when you're ready. Check your work against mine. I know that I've got 1.25 moles of hydrogen at standard temperature and pressure, and I need to convert that into liters. I always start by taking the number and units I've been provided, in this case 1.25 moles of hydrogen. I know that 22.4 liters of a gas at standard temperature and pressure are equal to 1 mole of a gas. So I've got my moles to cancel out. It leaves me with liters, and to the correct number of sig figs, I calculate 28.0 liters. Here are some more conceptual questions about molar volume. No calculations necessary. Which balloon has the largest volume? Which balloon is the heaviest? And which balloon contains the most molecules? Keep in mind that each balloon contains 1 mole of gas at standard temperature and pressure. Pause the video and see if you can come up with answers to these 3 questions, along with a brief explanation. Let's take a look at question number 1. Which balloon has the largest volume? Well, they all contain 1 mole of gas at standard temperature and pressure, so they are all equal. They should all have volumes of 22.4 liters per mole. Which balloon is the heaviest? Okay, well here, knowing that there's 1 mole of gas at STP, that's not going to help us out a ton. We're going to have to do a little bit more math. I need to find the molar masses of H2, CH4, and NO2 respectively. I come up with roughly 2 grams per mole, 16 grams per mole, and let's see, NO2, that's going to be 32, 46 grams per mole. So that takes care of that question. The nitrogen dioxide balloon is going to be the heaviest, as NO2 molecules have the greatest molar mass. And finally, which balloon contains the most molecules? Well, we're told 1 mole of gas. So if they each have 1 mole of gas, we know that they all contain the same number of molecules. They're all equal. And they're all going to have 6.02 times 10 to the 23rd molecules. All right. Mole conversions are going to be a really important aspect of what we do, not just for the remainder of the unit, but for really the rest of your study in chemistry. The mole comes up continually. Chemists love the mole because it's able to connect so many units. We can talk about number of atoms or molecules. We know that 6.02 times 10 to the 23rd items or things are going to be equal to 1 mole, and we can use this fraction, either the right side up or upside down, however you'd like to think of it, to get out of things like moles and into actual counting numbers. That's something that would be impossible to do without the mole, as atoms and molecules are far too small for us to see and count on our own. We know that the mole also can be used to connect mass. We know that we can calculate the molar mass of a substance, basically by finding its mass in grams, and using the periodic table. So we did examples with water. H2O, 2 hydrogens plus 1 mole of oxygen will give us a total of 18 grams per mole. And we can use that to convert. So I've just represented that as molar mass in grams over 1 mole. Again, don't forget, you can flip that fraction upside down if you need to. And finally, we talked about molar volume. We know that a mole of gas at standard temperature and pressure, regardless of its identity, is going to occupy 22.4 liters. That gives us yet another conversion factor, 22.4 liters, again, of a gas over 1 mole. So we can use these conversion factors to make all sorts of unit conversions as we're going to need them. So let's go ahead and try some practice problems. So you have these questions in your workbook, and they're going to require you to make conversions using those 3 different conversion factors that we just talked about. So let's say you've got 91.05 liters of argon at standard temperature and pressure, and you decide you want to know how many atoms are present in that sample. We're going to start the same way we start all dimensional analyses, by writing down the number and units that were provided. I don't know how to get from liter directly to number of atoms. I'm going to need to use the mole to convert. I know that at standard temperature and pressure, 1 mole of a gas, and argon is a gas, will be equal to 22.4 liters. So I can use this fraction, or conversion unit, to get liters to cancel out and leave me in moles. The question wants me to solve for number of atoms. So I know that there are 6.02 times 10 to the 23rd atoms in 1 mole. If I put 1 mole in the denominator, I can get mole to cancel out. And I'll put Avogadro's number up in the numerator. I've canceled out all my unwanted units. I've got the units that I need in the right location. Now it's just a matter of using my calculator. So I've got 91.05 times 6.02 times 10 to the 23rd. Be careful about how you enter that in your calculator. And divide that answer by 22.4. And that should tell you how many atoms are present. When I do the math, I get 2.447 times 10 to the 24th atoms. Make sure that you're careful with sig figs. Ooh, I did not follow my own advice. I probably, because there are 3 sig figs in 6.02 times 10 to the 23rd and 3 sig figs in 22.4, should cut that off at 2.45 times 10 to the 24th atoms. All right, why don't you go ahead and try letters B and C. I'll start going over letter B, so if you think you've got it, you can just either pause this or fast forward this and check your work against my answers. All right, so for letter B, I've got number of atoms, and I'm trying to convert into mass in grams. So I know that I've got 7.51 times 10 to the 22nd atoms of lead. I want to get out of atoms. I know that 6.02 times 10 to the 23rd atoms equals 1 mole. I can get rid of atoms, and now I'm in mole. I'm trying to get mass in grams, so I cannot do this without using my periodic table. I can look up the molar mass of lead and see that it is roughly 207.2 grams per mole. That'll get moles to cancel out, and I'm going to be left with just a math problem now, and I end up with 25.8 grams. I take my 7.51 times 10 to the 22nd, multiply it by 207.2, and then divide that by 6.02 times 10 to the 23rd. I can double check, make sure this makes sense. I know I've got less than a mole of lead atoms to begin with, so I better have less than 207 grams, and I do. Right, and for the last one, 17.6 grams of helium. And I'm trying to get that into liters at standard temperature and pressure. All right, I know that I need to first get to the mole. When in doubt, take the number you've got and convert it to moles. It's a really great first step, and a lot of times that's the correct way to go with this. So I've got it in grams. I need to know the molar mass of helium, which using a reference table or periodic table, I can find that that's 4 grams. Now I'm out of grams, and I'm into the mole. I'm trying to get to liters. So 1 mole of any gas at standard temperature and pressure is equal to 22.4 liters. That'll cancel out mole and leave me with liters. So I'll take 17.6 times 22.4 and then divide that answer by 4, and I should come up with 98.6 liters. Okay, the answer key for the remainder of these problems are online. I highly recommend going through and doing some practice. We're really going to build on this idea of mole conversions in future lessons. So it's really in your best interest to get this to the point where it feels almost second nature. All right, well, thank you for tuning in, and I hope you found this helpful.